Hi, welcome to another edition of Calculus 2. Today we are going to talk about the integral test and p-series. Let's go ahead and take a look at this interesting topic. So we started talking about sequences, and then we said a series is a sum of the elements of a sequence. For the first type of series that we looked at, geometric series, we could easily sum it up and figure out if it converges or diverges. But that is rather unusual for us to be able to actually find out the exact value of a series. What we have in mind now is to find some approximations for the sum of a series and methods for figuring out if the series actually converges or diverges. We are going to have a long list of variety of tests that will inform us about these properties, and perhaps the easiest one of them is the so-called integral test. And based on that we are going to have the p-series test as well. So let's, for example, take a look at a series here, sum of 1 over n squared plus 1 from 1 to infinity. There's another area of mathematics we come across summations, and that's when we were doing integrals. Integrals were actually summation of the area of rectangles on the graph of a function. So it's not surprising that two of these things go hand in hand. When I want to investigate sum of a series, I might as well investigate the area of the curve for a function that matches the terms of the series. So if it is possible for us to find a function that matches the elements of this series, we have an advantage in actually attacking the series and finding some information about it. So to study if this series converges or diverges, we might as well study if this integral converges or diverges. We have looked at these integrals under so-called improper integrals, so perhaps you want to take a look at that and see what's the effect of having infinity as one of the boundaries. But the idea is essentially very intuitive. So the requirement for doing this match is that if you have terms of your sequence as an, then you have to look at the function that matches that. That is, a sub n has to be f of n. So this function 1 over x squared, of course if I put x to be some whole number n, and this will be same as that. In addition, we are going to require certain basic properties of this function for our comparison to work easily. The function has to be positive, continuous, and decreasing for our approximation to work. Let's go ahead and see. If I'm adding the terms of this series, so for example I go at n equal to 1, I get 1 over 1 squared plus 1, that's 1/2. If n is equal to 2, that's going to be 1/5. If n is 3, that's going to be 1/10, and so on. So these are some heights I have in mind, and I might as well graph them. So this is at n equal to 1, I'm at this location. At n equal to 2, I'm at this location. At n equal to 3, at this location, and so on. At n equal to 4 will be down here, almost close to horizontal axis. So the function that matches this terms of the series is 1 over x squared plus 1. That would be this blue line that goes through these points of the series. Now how do we compare one against the other one? We are going to make rectangles, and the rectangles are going to help us to compare areas. So if this height is the first term of the series a1, if I make a rectangle out of it, the area of this rectangle is going to be the base of it, which is 1, times the height of it, which is a sub 1, and so the area is actually same as the first term of the series. So when n is equal to 1, 1/2, the term is 1/2. Well, the area of this rectangle is also 1/2. At n equal to 2, the height becomes 1/5. That's 1/5. The area of this rectangle is also 1/5. And so on. Here is at n equal to 3, the height of the term in the series is 1/10. Area of this rectangle is also 1/10. We see that the sum of these yellow rectangles is more than the area underneath the curve. So if I add up A1, A2, and A3, the first three terms, it's going to be more than the area under the graph of f of x from 1 to 4. Okay, I'm going up to 4 here, but I add up the first three terms of the series. So sum of A1, A2, A3 is more than area from 1 to 4 of f of x dx. On the other hand, if I come ahead and build the rectangles underneath the curve, so here I'm making these blue rectangles. First one of them is at the second term of the series A2. The next one is A3. The next one is A4, and so on. These are all sitting below the graph. So sum of the area of these rectangles is going to be less than the area under the curve. So area from 1 to 4 underneath the curve is going to be more than the sum of these blue areas. So it's going to be more than A2, A3, and A4 combined. In the same manner, I can make more rectangles. I can go up to 10 or 100 or up to n. And then I'll have the following. The area under the graph of a function is going to be from 1 to n is going to be less than sum of all the elements of the series from 1 to n minus 1. We are missing the last term here, and it's more than, we skip the first, start from A2, go all the way to AN. We can rearrange this thing and say, for example, this area of under the curve, if I add AN to it, I'm adding AN to both sides of this. So that sum is less than the partial sum from 1 through n. And if I add A1 to both sides, A1 through AN again is this term, and that sum is less than A1 plus the integral from 1 to n of f of x dx. Okay, what does this tell us? A couple of things. One is that if I want to investigate the partial sum, I can do it through these integrals. That tells us one way of coming up with the estimation for the partial sum. Second term, if the integral diverges, meaning when n goes to infinity, if this integral diverges, then we know that the series will diverge. If the integral converges, then we know that the series is going to converge. So the two of them go hand in hand. If one converges, so does the other one. If one diverges, so does the other one. The only thing that we need to be careful about is to make sure that the function we have chosen shows these three properties, that it is positive, continuous, and decreasing. Typically, you don't have much of a challenge to show that it is positive and continuous. Typically comes from the problem immediately. When it comes to decreasing, how do we figure out if a function is decreasing? Remember from calculus 1, we had a standard method for establishing that the function is decreasing. Let me see if you can pause for a second and tell me, how would you tell if a function is a decreasing function? Did you remember what you do? Of course, if you have a function increasing versus decreasing, increasing matches the property that the derivative is positive, and decreasing matches the property that the function has a negative derivative. So in addition to these properties, first of all, you want to have the function to be differentiable, and it should be easy for you to tell if you are in an increasing range or you are in a decreasing range. One additional remark for making this type of a comparison, the comparison should hold from some place on. Sometimes the very first few terms might not be a good match, but down the road at the tail of the series, the matching might be exactly what you want. We are going to see some examples of these things in the problems that we are going to do. Let's go ahead. For example, let's take a problem. The idea is to apply integral test to find out if the following series diverges or converges. So suppose we have the following. Sum of n from 1 to infinity of 5 divided by 3n plus 1. So what sequence are we talking about? This would be 5 divided, first term is going to be 4, next time is the 7, and the next one is 10, and so on we go. The question is, would this sum converge or diverge? We might even want more information if it diverges. For example, at what point does it exceed 100 or 1000 or something like that? All of that can be obtained, of course, in an approximate fashion by the integral test we have. So here we say, okay, the matching function is rather obvious. It's 5 over 3x plus 1. So if the function that you have here is one of those basic functions you see in calculus, the conversion from n to x is immediate. Next, is this a legitimate function for us to consider? Well, legitimate meaning, is it positive, continuous, decreasing? And in addition to that, it would be nice if it is differentiable. Well, it's obviously it's a continuous function, is differentiable and everything. All we need to check is that it is a decreasing function. If it was fluctuating and such, our comparison would not work easily because our rectangles would not simply sit underneath the graph or uniformly above the graph. We'll have a hard time making a comparison. So as a check to see if my function is decreasing or not, I take a derivative. Of course, here derivative of numerator times denominator is 0, minus derivative of denominator, which is 3, times numerator is 5, over 3x plus 1. Well, that's obviously a negative quantity wherever it exists. It definitely exists for positive x's, and it is a negative quantity. So this is a decreasing function. So this tells me the f that I want to use, f is decreasing, and therefore I can compare this series to this integral, from 1 to infinity of 5 over 3x plus 1 dx. Okay, now we have delegated the problem to an integration problem, and then we have to go to our toolboxes for integration, figure out how to do the integral. We have learned all sorts of ways of integrating function, and typically this is not a very challenging step of these problems. In this case, you notice that well, it we might as well start with the indefinite integral 5 over 3x plus 1 dx. By a simple u substitution, we are going to be done with this problem. If u is 3x plus 1, then du is 3 dx, and therefore dx is simply 1/3 of du. Our integral becomes 5 over u. This is du over 3. So it becomes 5/3 of logarithm of absolute value of u plus a constant. So that is 5/3 of logarithm of, the value of the function for me is positive, so I don't need the absolute value. It's 3x plus 1 plus a constant. Okay, so that is how to do the indefinite integral. Then we come to this issue. You remember, for improper integrals, the idea was that we would calculate the integral up to certain variable quantity and then let that quantity go to infinity. So the standard approach was to calculate the integral from 1 to b of 5 over 3x plus 1 dx. So that meant take this answer 5/3 of logarithm of x plus 1 and evaluate it between these two limits and see that this is 5/3 of logarithm of, this is b plus 1, and then minus 5/3 of logarithm of 2. Then the integral from 1 to infinity is the limit of this when b goes to infinity. Well, when b goes to infinity, this logarithm of infinity will be infinity. This whole thing becomes infinity, and that integral is going to be infinite. So in short, if you just have a logarithm of x or an expression similar to that, then the integral ends up being infinity. So what does that imply for us? If the integral becomes infinite, the sum will also become infinite, and therefore we can say that the series diverges. So what does it mean in this case? This is a case that we have area under the curve. We have established that to be infinite. And now we are saying, well, sum of all of these a's is going to be even more than what is the area under the curve. Therefore, the sum also goes to infinity. Well, let me show you also in the context of a demo that's a little bit cleaner than the pictures I have drawn. So here's a simple demo. The function is a bit different, but just to keep it simple, I have it like 1 over x plus 1. It can be any function you have in mind. So the graph of this function is this orange color line or orange brown color that you see here. Okay. The area under this we have established to be infinity. That's the our integration shows that the area is infinity. We can show our series by these green rectangles. The area of each of these rectangles is equal to one of the terms of the series. So the sum of the series is going to be this area underneath this kind of stair-step looking curve. Well, that area is whatever it is more than the area underneath the curve. And since the area underneath the curve is infinity, the area under this green portion has to be infinity as well. So that is how to establish if something is divergent. You can also use this to find out approximately how many terms of the series does it take for the sum to be more than some given number. Suppose I ask you, how many terms do I have to add to be sure that the sum is more than, say, 500? Well, you can use the integral test to give an estimation for that answer. Let's go ahead and look at some problem with a bit more flavor. Let's look at another one. Here's another question from your textbook. It says, investigate the following series for convergence or divergence. So for example, it says I have the following series: logarithm of 2 over 2 plus logarithm of 3 over 3 and logarithm of 4 over 4. You might be wondering why I didn't put logarithm of 1 over 1, but well, logarithm of 1 is 0. If you wish to put it, that doesn't change anything, because this is, you remember, that's 0. So if you want for nicety's sake to add that as well, that's fine. So the question is, does use integral test to determine if this converges or diverges. So use integral test to determine if the corresponding series, if the series converges or diverges. So in this case, the formula for the term of the series is not given to you, but in this case it's rather obvious what is intended here. What is intended, of course, it's by consensus that we say we are calculating logarithm of n over n. Now again, if you want to start at 1 or you want to start at 2, yeah, it doesn't make any difference here. And in general, adding or removing first few terms of a series has no influence on the issue of convergence or divergence. So you are always free to set aside any first beginning few numbers of the series if you wish. Okay, so to keep everything looking nice like previously, let's say from 1 to infinity, we are investigating this. Well, it's easy to match this against the function, because all of these have the corresponding functions from calculus. In this case, it's going to be just logarithm of x over x. So these two, meaning the integral from 1 to infinity of f of x, in this case logarithm of x over x dx, this is going to have same fate as this one. If this converges, that one will converge. If this one diverges, well, that one will diverge. Now, logarithm of n over n is not as simple as, say, geometric series for us to go add it up. So this is a kind of a comparison we are using against something that's more familiar, hopefully, for us, and hopefully this will shed some light on what's going to happen in this case. So well, logarithm of x over x, what do we do in that case? Let's go ahead, investigate this logarithm of x over x. This is a problem you have seen in calculus 1 and perhaps recently again in the context of techniques of integration. Simple substitution will do the job here, because if you take u to be logarithm of x, then du is simply just 1 over x dx, and our integral simply becomes logarithm of u. Okay, so excuse me, let's see. So this becomes this is u, and dx over x is just du. Antiderivative of that is, of course, just excuse me again, antiderivative of that is u squared over 2 plus c. So integral of logarithm of x over x dx is simply logarithm of x squared over 2 plus a constant. Now if I want to calculate area from 1 to infinity, I have to plug 1 and infinity in this and subtract them from each other. What was our procedure for improper integrals? you say limit of logarithm of, now we put a b here or anything else you wish, logarithm b squared over 2 as b goes to infinity. Well, as b goes to infinity, this quantity is going to be infinite, and our integral simply going to go to infinity. What does that imply? It implies that this sum is also going to go to infinity, and as a result we are going to declare this thing as a divergent series. Again, a side problem here would be, okay, if it is divergent, it means it's going to exceed any number that you set. For example, I might ask, at what point would it exceed, at what point would the sum exceed 1000, or at what point does the sum exceed 10,000 and such. So we can use this estimation here to get a guess where the crossover is going to happen. And so on. So we see a variety of problems here. Let's go do another test. Suppose the question is, what is the fate of the following series? 1 over 2n plus 3 cubed and running from some starting number to infinity. So we say this goes hand in hand with integral of 1 over 2x plus 3 cubed. Before we go here, let me see, I forgot one thing to establish. When we do this integral test, there is one thing we need to check, is that our function is decreasing, and the easiest, the most common way of doing that is to show that its derivative is negative, and I forgot to include that in this step. So let me just put it here. What's the derivative of logarithm of x over x? So that expression, when it converts it to the continuous variable x, we go and check that its derivative has to be negative for it to be a valid check. So in this case it's easy. Derivative of numerator is 1 over x times denominator, that is just 1, minus derivative of denominator is 1 times numerator, that's logarithm of x over denominator squared. Okay, what is the fate of the numerator? At x equal to 1, this is positive, but at x equal to 2, this starts being negative and stays negative like that. So we say this quantity is negative for x's that are larger than, okay, so x, well, let's go ahead, set the numerator of this thing equal to 0. We see that logarithm of x has to be equal to 1, so x has to be equal to e. Up to e, this numerator is positive. After that, it's going to become negative. So for x, what is e? Remember, e is 2.7 and so on. So definitely for x's that equal to larger than 3, this expression is negative. So even though at the very beginning, for a short time, this derivative is positive, it quickly turns into negative and stays like that. And we said the first few cases, it does not matter for our testing. It's the tail of the sequence that is important for us. So for x is larger than or equal to 3, the derivative is negative and our test is valid. Let's go ahead do the following test here. So again, I do a u substitution. This integration is from 1 to infinity. I take u to be 2x plus 3, so du is 2 dx. Therefore dx is du over 2. The integral from for this function 2x plus 3 cubed dx turns out to be 1 over u cubed times du over 2. So that's 1/2 of the integral of u to power of minus 3 du. Integral of that is 1/2 u to power of minus 2 over minus 2 plus a constant. In short, that is going to be 1 minus 1/4 of u squared plus a constant. So integral from 1 over 2x plus 3 to power of infinity is going to be minus 1/4 of 2x plus 3 squared. If I want to calculate the integral from 1 and stop at some location b, this is going to be 1 over 2x plus 3 cubed is equal to, we go ahead and calculate this between 1 and b, so I plug b in this thing, becomes 1 over minus 4 times 2x plus b, 2b plus 3 squared, then minus 1 over minus 4 of x now is 1, so it becomes 2 times 1 plus 3 squared. Cleaning this up, I can put the factor of 1/4 outside. This becomes 1 over 5 squared, and this is 1 over 2b plus 3 squared. Now what happens when b goes to infinity? When b goes to infinity, this fraction goes to 0. We are left with just this term. We can use it to approximate the sum, but right now all that we care about is that so we have the following conclusion: 1 through infinity of 1 over 2x plus 3 cubed is convergent, is a convergent integral, because it actually converges to 1 over 5 squared, so that's actually 1 over 100. So we have established that the integral converges, therefore we can conclude that this in series converges. Not only that, we can compare it against the value of that integral and get an approximation for what this thing is. Okay, one of the most important series whose convergence or divergence can be established in this fashion is a so-called P series. P series simply refers to the following: 1 over 1 to the power of p plus 1 over 2 to the power of p, 1 over 3 to the power of p, and so on. So in short, this is 1 over n to the power p added up from 1 to infinity. Using the above test, we can show easily that if p is larger than 1, this p series converges. You simply compare it against the integral of 1 over x to the power of p. If p is less than or equal to 1, then the p series diverges. So for example, 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, and so on. This one converges. Actually, very similar to what we just did, very similar to this, slight difference in the term that we have over there. But if p is less than or equal to 1, well, p equal to 1 would be harmonic series we looked at last time. P less than 1, for example, an example of that would be power 1/2, which you can convert it to radical if you wish, 1 over radical 3 and so on. This one diverges, it goes to actually infinity. Okay, this is gonna be this result is gonna be one of the very important ones we are going to use in checking many series from here onward. That's going to give us a tool that's going to be faster than what we have here. The integral test takes a little bit of time because you have to apply the integration and such, but we are going to see in the next lectures on such. P-series gives us a faster way of coming up with a conclusion at the expense that it's not going to give us an easy way to actually get an estimation, just quick verdict as to the series converges or not, but that's about it. But just to indicate how important this P-series is, let me show you some of the articles online. There is a very famous function in mathematics, perhaps in some sense the most famous question in mathematics revolves around this particular function. The terminology is a little bit different. Instead of that power p we had before, is a power is indicated by s, and the whole series is given a name. It's called a Riemann-Zeta function. Riemann is a German mathematician, and Zeta is just a letter of alphabet, Greek alphabet, which is shown is like this. So quite a bit of mathematical research has gone into investigating the properties of this particular function. It is a whole area of mathematics occupying many books and conjectures and so on. So what we are touching on right now is has some connection to that issue too, but you're going to see that in more advanced classes in future years, hopefully. Okay, I stop here. Look for more exercises related to this section. Try to line up your reasoning whenever you are applying the integral test. Make sure you do not skip the section that you need to show that your function is actually decreasing. In this case, actually I forgot it myself to in this case it's rather obvious that the function that we are looking at is a decreasing function, but just to emphasize that we need to show this thing formally, 2x plus 3 cubed. Well, what is f prime? If f prime is negative, then I know my function is decreasing. In this case, it's rather obvious that numerator increases with x, therefore the fraction is going to decrease. But just to be complete, here maybe the best thing to do is to write this thing in the terms of power. So its derivative is going to be the exponent, which is minus 3, times the derivative of the base, which is 2, times 2x plus 3, and then we have to decrease this exponent, so it becomes minus 4, and if you want to write it nicely, it becomes minus 6 over 2x plus 3 to power of 4. Well, this expression is always negative. Whenever it exists, it's negative. So we are done that the function f of x that we are using, f of x is decreasing, and of course again in this case we could easily see that at the start that it is actually a decreasing function, but just make sure you make a mention of it that you have tested your function to be decreasing, and then your test will be solid. Okay, until next time, good luck and God bless.